Hello, everybody. Thank you very much for joining this talk. My name is Oren, and this is a joint work with Professor Leonid Barenboim. Today, I would like to talk about some last results we achieved in my research on backup placement, specifically about backup placement in WSNs in the network management distributed setting. My talk will be divided into 3 consecutive contents. We will start with some intro to the topic, including previous results. Then we will move to define the problem in the new setting of distributed network management. Finally, we will present our new approach to solve this problem using an adaptive clustering refinement, which actually managed to achieve more than just good backup placement. Let's start with some intro. First, we formalize the dynamic network management setting configuration. In this configuration, computation proceeds in synchronous rounds, and all IDs are distinct. Each round in the distributed algorithm consists of 3 stages. 1, each node in parallel to other nodes receives messages sent to it by its neighbors at the previous round. 2nd, each node in parallel to other nodes performs a computation. 3rd, each node in parallel sends messages to its neighbors. The dynamic network management setting is based on the congest setting with the following additional features. Each vertex has a cost that accumulates during the round of the execution. In each round, each vertex V may add edges to a certain distance K in G. A vertex may also remove edges that connect it with vertices outside of its immediate neighborhood. So finally, we reach to the backup placement problem. This problem was introduced by Halderson, Kohler, Pachemir, and Ravitz in 2015. In terms of graph theory, the problem in its simplest form is defined for a network graph GVE as follows. Each vertex V in V is selecting a neighbor such that the maximum number of vertices in V that select the same vertex is minimized. The problem is well motivated by computer networks whose nodes may have memory faults and wish to store backup copies of their data at neighboring nodes. But neighboring nodes may incur faults as well or be overflowed. And so the number of nodes that select the same backup node should be minimized. This way, if a backup node incurs faults, the number of nodes in the network that lose data is minimized. So after we got familiar with the problem and the new setting, let's see why we need to redefine the problem given those settings and how this change of setting can be helpful. Until recently, Halderson and ACR Algorithm remained the state-of-the-art for general graphs, as well as for specific graph topologies. Very recently, this was improved by Langley, Bernstein, and Asadi, who devised an algorithm with an O1 approximate backup placement for general graphs. Barenboim and Oren obtained significantly improved algorithms for specific graph topologies. Specifically, they show that O1 approximation to optimal backup placement can be computed deterministically in O1 rounds in wireless networks, certain social networks, fluffy graphs, and more generally in any graph with neighborhood independence bounded by a constant. On the other end, they considered sparse graphs such as trees, forests, planar graphs, and graphs of constant arboricity, and obtain constant approximation to optimal backup placement in O-log and deterministic rounds. Barenboim and Oren also devised an additional algorithm for dense graph topologies, including unit disk graph, unit ball graph, line graphs, graph with bounded diversity, and many more. This algorithm requires just 1 round and consists of just a single very simple operation. Surprisingly, such a simple round strategy turned out to be very efficient for backup placement computation in dense networks. Not only it improves the number of rounds of the solution, but also the approximation ratio is improved by a multiplicative factor of at least 2. What we did learn from the previous studies is that the most efficient backup placement policy can be formed in oriented low-degree trees and in graphs with relatively small bounded independence. However, in the dynamic network management setting in which vertices can influence the transmission range, those previous results are less efficient, as the bounded independence could be relatively large and a performance degradation will occur. Thus, in said setting, it is suitable to form low-degree trees, which interconnect the different active parts of the entire network in order to achieve good performances. This makes it possible to obtain a balanced backup placement while optimizing connectivity, energy, memory, and storage space. To this end, we redefined the problem in terms of WSNs. Our approach towards the solution relies on the reconfigurable nature of the whole network, which eventually would be able to balance the load in an overloaded network properly and accomplish a proper backup placement. We investigated whether hierarchical WSNs can benefit from a distributed constant refinement of the network structure based on the idea that a load balanced network would be more energetically optimized. Unlike other WSN clustering algorithms that do not recluster the network after deployment, our hypothesis is that it is advisable in terms of prolonging the network lifetime to adaptively recluster specific regions that are triggered significantly more than other regions in the network, while we consider sensors as triggered if it's been activated by external events to perform sensing, processing, and transmission actions. By doing so, it is possible to minimize or even prevent the premature death of cluster heads, which are heavily burdened with sensing and transmission actions, much more than other parts of the WSN. Let's see how this ACR tree works. The first problem we are focusing on is the ACR tree problem. ACR trees make it possible to efficiently gather data from the triggered vertices into the destination node, which is the root of the tree. The ACR tree T must fulfill the following goals in the end of each step. In view of the above mentioned considerations, an ACR tree has several advantages. It makes it possible to improve energy consumption while bounding the load on parents, which originated from their children. In addition, information propagates quickly to the root thanks to the bounded height of the tree. This is in sharp contrast to certain extreme scenarios, such as connecting all nodes directly to the root, which causes excessive power consumption and load, or maintaining a fixed tree of def log n all the time, which may be much higher than needed, which causes slowdown in information aggregation by the root. Let's see how the algorithm makes decision based on local behavior of clusters rather than taking into account the global behavior of the entire network. In this way, we can obtain efficient update time of our algorithm without compromising energy efficiency significantly. The algorithm is executed by all vertices V in V in parallel. The main idea of the algorithm is the following one. Once an energy use of a cluster becomes higher than a certain threshold, we partition the cluster into C subclusters, i.e. into C coordinates whose size is smaller by a factor of C. The cluster partition is performed if the number of trigger vertices in the cluster is greater than C. This results in adding new cluster heads nodes to the ACR tree as leaves that becomes the children of former leaves from a previous step. These new leaves correspond to the newly formed clusters. Then this process is repeated recursively by checking in parallel whether each of the new smaller clusters has more than C triggered vertices. This refinement results in a better energy use in each such newly formed cluster, since the transmission diameter becomes smaller. In other words, we balance clusters of excess energy use by decomposing them into smaller clusters that require less energy. An opposite operation in which some clusters are merged into larger ones may also be required. This happens when several clusters have less than C triggered vertices altogether and can be merged. This is performed using the ACR tree as follows. Each vertex in the tree whose all children are leaves checks how many triggered vertices there are in clusters of these leaves. If the number of such trigger vertices is at most C, then these clusters are merged into a single one, and the leaves are removed from the ACR tree. The parent of the leaves becomes the cluster head of the new cluster. Then this process is repeated recursively. Consequently, the energy use of vertices in the newly formed larger clusters may grow, but the tree distance between the roots to some leaves decreases. Our algorithm employs a subroutine for determining how many triggered vertices there are in a cluster without requiring transmission between all of these vertices and the cluster head. This can preserve a significant amount of energy. And that's about it. Let's see an example. In this one, we can see the formation of an ACR tree. The root node in blue is associated with the entire vertex at V, and it is in the center of the plane, which is partitioned into coordinates 4 times while C equals 4, resulting in a tree of 16 cluster heads. Now, that is a pretty simple example. Let's imagine this process in different regions of the network in refinement and coarsening simultaneously, on and off constantly. In order to prove that the algorithm works as we think, we prove the following theorems. We learned from those theorems that the maximum energy consumption in the ACR tree is n log n. We know that in case where the tree is not used, an extreme scenario is when all vertices communicate directly to the root. In such case, the overall energy consumption is theta n squared, which is significantly larger than the ACR tree one. The above presented ACR tree immediately gives rise to a basic backup placement, as each vertex can send its backup to its parent and the root to one of its children. In the network management setting of a grid, a backup placement of load at most C plus 1 equals 5 can be maintained within log squared n update time and an ON log squared n energy consumption. Thank you for listening.